right, thank you very much. My name is Gratz, and I'm here to tell you today a little bit about our observations and model analysis of enhanced oxidized mercury that we observed in the free troposphere during the NOMADSS campaign. And before I begin, I just want to acknowledge the contributions from my co-authors and our other NOMADSS collaborators, and also recognize the funding provided for this project by the National Science Foundation. Oh, this one here. There we go. Good, that's confusing. 2 keywords to choose from. So mercury is a hazardous neurotoxin and is introduced to the ecosystem primarily through the deposition of oxidized mercury species. Total atmospheric mercury is comprised largely of gaseous elemental mercury, which can persist in the atmosphere for quite a long time, on the order of weeks to months. And the conversion to the more soluble oxidized form is how mercury can be introduced into the ecosystem. Now, the current thinking is that atomic bromine is the dominant global oxidant of gaseous elemental mercury, but there are very large uncertainties in this chemical mechanism and in the associated kinetics. So there's a great deal of uncertainty as a result in the global cycling of atmospheric mercury. Currently, there are only a handful of observations, either ground-based or airborne, of oxidized mercury in the free troposphere. But the presence of oxidized mercury in the free troposphere is very important for the global distribution of atmospheric mercury, as we know that air masses in the free troposphere can undergo long-range transport. So better constraining the sources and distribution of oxidized mercury in the free troposphere is very important to understanding the global mercury cycle as a whole. So this was one of the key scientific objectives of our work on the NOMADSS campaign, was to try to understand the distributions and chemical transformations of mercury in the free troposphere. In order to do this, we measured atmospheric mercury species on board the National Science Foundation and National Center for Atmospheric Research C-130 aircraft. The NOMADSS campaign took place during summer of 2013 and was located in the southeastern U.S. Our instrument for measuring atmospheric mercury species is the University of Washington's Detector for Oxidized Mercury Species, or the UW-DOGS. This instrument is able to continuously measure total atmospheric mercury and gaseous elemental mercury with a time resolution of 2.5 minutes. And we quantify oxidized mercury by the difference between total mercury and gaseous elemental mercury. One of the unique features of the UW-DOGS is that we're able to calibrate it with gaseous elemental mercury in flight. So for all of the NOMADSS flights, we calibrated the dogs on the ground, in flight and post-flight, with a gaseous elemental mercury permeation source. We've also done a number of tests with the UW-DOGS in our laboratory, both for elemental mercury and for mercury bromide as a surrogate for oxidized mercury compounds. And additional details on the UW-DOGS can be found in a paper by my colleague, Ambrose, in ES&T. There were a number of additional measurements made on board the C-130 as part of the NOMADSS campaign. The ones I've listed here are the ones that are most relevant to the data that I'll be presenting today, which include ozone, CO, water vapor, and bromine oxide, as James just reported in the previous presentation. So we conducted 19 research flights during the NOMADSS campaign, and you can see the flight tracks for those particular flights in the plot on the left. And overall, on these 19 research flights, we found that oxidized mercury concentrations were higher in the free troposphere than they were in the boundary layer. And today I'll be presenting 2 specific cases where we saw particularly enhanced oxidized mercury. The first is Research Flight 6, which is the same flight that James just reported on. And this was a flight where we flew to North Texas and spent about an hour and 45 minutes flying in the free troposphere at a relatively constant altitude of 6.8 kilometers. The other flight that I'll talk about is Research Flight 16, where we did a vertical profile over the Atlantic Ocean off the coast of South Carolina, and also saw enhanced oxidized mercury. So beginning with Research Flight 6, I'm showing here our observations of oxidized mercury, and on the bottom plot you can see the altitude of the C-130 aircraft as well as the water vapor measurements. And the box highlighted in gray is that period that we spent flying at a relatively constant altitude in the free troposphere over Texas. Our average oxidized mercury concentration in that particular band was 266 picograms per cubic meter. And again, we found that bromine oxide was particularly enhanced in that air mass as well. We also found that that air mass had very low ozone, carbon monoxide, and water vapor. So it was extremely dry and very clean. This suggested to us that the air mass was not recently influenced by boundary layer air or combustion emissions, but also, as James reported, we don't see any indication that there was any stratospheric origin of this air mass, and so it really appears to be a free tropospheric air mass, very clean and very dry. Now moving over to our case over the Atlantic. In this case, rather than flying at a constant altitude, as I mentioned, we conducted a vertical profile up to just above 4 kilometers over the ocean. We saw a particularly oxidized mercury-rich air mass between altitudes of 1 and 3 kilometers over the ocean, and I've highlighted that area again with the gray box. The black points on the figure represent the average measurement, and the arrow bars represent the range in our measured concentrations. So in that air mass between 1 and 3 kilometers, we measured on average 485 picograms per cubic meter of oxidized mercury, with concentrations up to 680 picograms per cubic meter, which was the highest value that we measured during the entire NOMADSS campaign. During this profile, again, we also saw low concentrations of carbon monoxide as well as a number of VOCs, which again suggested that the air mass was not recently influenced by anthropogenic emissions or boundary layer air. Throughout this vertical profile, oxidized mercury was also anti-correlated with elemental mercury as well as water vapor. And this suggested to us that the air mass saw relatively recent oxidation, again in a dry air mass, and varying levels of chemical processing with altitude. So to get an idea of what the origin was of this enhanced oxidized mercury that we observed in the two cases, we examined high-split 7-day back trajectories for the mercury-2 rich air masses. For research flight 6, we determined that the air mass again, was of free tropospheric origin and spent several days circulating and subsiding within the Pacific high-pressure system, and then subsiding to our measurement location over North Texas. And the time that this air mass would have spent circulating within the high-pressure system would allow sufficient time for elemental mercury oxidation. For research flight 16, we suspect again from these trajectories that the air mass originated in a high-pressure system over the Atlantic Ocean, which you can see with the trajectories on the right-hand side. And again, a slight difference in this air mass is that it appears, given the relationship between oxidized mercury and elemental mercury, that the oxidation was relatively recent, given the strong anti-correlation between the two species. So to better understand the origin, in addition to using trajectories to understand the origin of oxidized mercury, we applied the GeoSchem mercury model. This is a global model, and in this case, we also applied a nested grid over North America. In the GeoSchem mercury model, oxidation of elemental mercury is performed by bromine atoms, and this is done by a two-step oxidation mechanism as shown here on the right. And so again, we used this model to try to investigate the origin of mercury-2 enhancements. And what we found initially is that in the two oxidized mercury-rich air masses on research flight 6 and 16, that GeoSchem does a very good job of reproducing our observations of total atmospheric mercury as well as water vapor and carbon monoxide, suggesting that at least on a broad scale that the model is doing a pretty good job of simulating the air masses that we were sampling, and it was important to note that it was at least quantifying the concentrations of total atmospheric mercury quite well. However, we did not find this to be the case for oxidized mercury. So here I'm showing our measurements of our measurements of oxidized mercury with the black points, and the green line here represents the output from the standard GeoSchem mercury model. And what you can see here is that the standard model largely underestimates our observations of oxidized mercury in the free troposphere over Texas. Now, we looked a little bit more into some of the measurements from this flight, and as James mentioned, we saw very high BRO on this flight, and we found that the GeoSchem model also largely underestimates the concentrations of BRO in this air mass. And now this is actually consistent with some other airborne measurement campaigns as well as satellite observations, that the GeoSchem model is largely underestimating observations of BRO. And so this, knowing that oxidation of mercury in the GeoSchem model is largely driven by bromine, this got us thinking that perhaps oxidation in the model is not as fast as it is in reality. So we performed two simulations to test for the possibility of faster oxidation. The first was to triple the oxidant concentration between 45 degrees south and 45 degrees north, and from 750 hectopascals up to the tropopause. And again, we chose this factor of 3 based on the differences between observations and model values of bromine compounds. Our other test to simulate to test for faster oxidation was then to triple the reaction rate constant. And what we found for research flight 6 is that both of these simulations do a much better job of reproducing our observations of oxidized mercury. So you can see here in the table on the right how our observations of oxidized mercury compare to the standard model and then to the 2 simulations for faster oxidation, and that we do a much better job with the 3 times bromine or the 3 times rate constant. Now, we found a different situation when we applied those simulations to our case over the Atlantic. So initially, we applied the standard model, the 3 times bromine and the 3 times rate constant simulations. And in all 3 of these cases, we found that the model is not even able to qualitatively produce our mercury observations. So as an example, I'm showing our profiles of oxidized mercury, elemental mercury, and total mercury from research flight 16. And the 3 times rate constant model is shown here with the orange dashed line, with that representing the average concentration, and then the shading representing the range. And you can see that for all 3 of the species, the model doesn't reproduce any sort of vertical variability in the concentrations. So we decided to explore this a little bit further, and we tested the fact that perhaps oxidation could be even faster. And so unfortunately for this flight, we did not have observations of BRO. The mini DOAS was not able to detect BRO on this flight due to the presence of clouds. However, we used the mini DOAS detection limit of 0.9 ppt and compared that to what the model was simulating, and found that even this detection limit is much, much higher than what we are observing. So just as a test, we tried increasing the BRO concentrations at least up to this detection limit of the mini DOAS, and found that when we use both the faster rate constant and higher bromine concentrations, we at least start to reproduce the structure of our measurements of oxidized mercury. So you can see that here on the left. Again, the black points representing the average concentrations at each of the altitudes of our vertical profile, and this purple line representing the average of this 3 times rate constant with 0.9 ppt of BRO. So we're starting to just see that at least with this faster mechanism, we can simulate the production of oxidized mercury in the free troposphere that we're not able to do with the standard model simulation. So to conclude, what these 2 cases have shown us or are suggesting is that elemental mercury oxidation in the atmosphere is significantly faster than what's currently used in most global mercury models. And to expand upon this beyond just these 2 cases, we need to investigate the conditions for mercury oxidation in large-scale anticyclones over both the Pacific and the Atlantic Oceans that were associated with the 2 mercury-rich air masses that we explored here. There's evidence that we need to better constrain our regional sources of atmospheric bromine. And we also need to determine the broader implications of faster oxidation for global mercury transport and deposition. And to expand upon that, I would invite you to attend a poster by my colleague, Viral Shah, which is tomorrow afternoon, in which he will look at all of our observations of oxidized mercury from the NOMADSS campaign and start to investigate the broader implications of faster atmospheric oxidation. And then I would also invite you to visit my colleague Jesse Ambrose's poster, which is actually up this afternoon, in which he's using measurements from the UW dogs, also from the NOMADSS campaign, but for a different purpose. He's looking at a comparison of inventoried and measured mercury emissions factors during the NOMADSS experiment. So with that, I'll conclude my presentation, and I'll take any questions that you have. That's a good question. That is a good question. I'm actually not sure if I can answer that right now, but that's a really good question that I'll discuss with my colleagues who are doing the modeling component as to what we think are the My expectation is that when we've looked at other bromine compounds from these two flights, such as bromoform, we found that the model is underestimating them as well. So it may be that just the regional sources of bromine are not as well constrained as we thought.